Question number 26. A copper block is hung over a beak of water by a spring balance, as in the figure. And they have given three positions of the copper block when the beak of water is slowly raising upwards. And the buoyant forces, the balance readings also were given, and they are asking for the correct expression. When an object is submerged in a liquid, there is a buoyant force acting on the object. This buoyant force is given by V rho G. V is the volume of the liquid displaced by the object. Rho is the density of the liquid and G is gravitational acceleration. Let's consider the positions of the copper block given in this question. Position 1, the block is partially submerged. Position 2, the block is completely submerged. When the block is completely submerged, the volume of the water displaced by the copper block is more than in position 1. So, therefore, B2 must be greater than B1. Position 3. The block is on the bottom surface of the beaker. Even if the block is on the bottom surface, the water displaced is same as in position 2. So there is no difference in the buoyant forces in position 2 and position 3. So B2 is equal to B3. Now we consider the spring balance readings. When the copper block is in air, as in the figure, the spring balance reading is equal to the weight of the copper block. When the copper block is submerged in water, the spring balance reading is equal to the weight of the copper block minus the buoyant force. Since B1 is the lowest, W1 must be the highest. W3 should be minimum since the string loses its tension when the block is in touch with the bottom surface. W2 should be in between W1 and W3. The answer is 5. Question number 27. A metal object is shown in the figure. Its cross-sectional area varies along its axis. The object is perfectly lagged and the two ends of the object are maintained at 100 degrees Celsius and 20 degrees Celsius. They are asking for the best graph which shows the variation of the temperature along the L axis. The rate of flow of heat along a rod is given by Ka delta theta over delta L. The rate of flow of heat is delta Q over delta T equal Ka delta theta over delta L. Delta Q over delta T is the rate of flow of heat and K is thermal conductivity, A is cross-sectional area, delta theta over delta L is temperature gradient. The rate of flow of heat along the rod is given by Ka delta theta over delta L. K is thermal conductivity, A cross-sectional area, delta theta over delta L is temperature gradient. So rate of flow of heat, that is delta Q over delta T equal Ka delta theta over delta L. The rate at which the heat enters the object is equal to the rate at which the heat leaves the object. So delta Q over delta T is constant. K is thermal conductivity is a constant. So A into delta theta over delta L is equal constant. By that we can take delta theta over delta L is proportional to 1 over A. The cross-sectional area of the AB section is greater than the cross-sectional area of the CD section. So the temperature gradient must be greater in CD than in AB. When you check for the gradients of the graphs, the fourth answer will satisfy that condition. That is, the gradient of CD is greater than the gradient of AB. Even without checking for the BC section, we can select the answer 4. That is, temperature gradient is proportional to 1 over cross-sectional area. Let's compare the cross-sectional areas of the rod with the gradients of the graphs. In BC section, the cross-sectional area decreases along the axis. So, the temperature gradient should increase along the axis. That is, the gradient of the graph should increase along the axis. So, obviously, the answer is 4. Question number 28. Three small conducting spheres carrying charges are located at the vertices of an equilateral triangle situated on a frictionless horizontal surface, as in the figure. Spheres at B and C are fixed and the sphere at A is free to move. They are asking for the possible path of the sphere A. In this question, they are asking only the path of the charge at A. So, no equations are required to solve this problem, but the knowledge of the magnetic field lines. Field line is a path of a unit positive charge placed in that field. You can draw field lines created by the charges at B and C. Along the BC points, the lines are straight lines and the direction is from C to B. The field lines are curved apart from BC. When you draw the field lines passes through the point A, you can see the path of C also lies on the same line. Since the charge at A is a positive charge, its path should be C. So answer is 3. Question number 29. A conducting loop is placed perpendicular to a uniformly increasing magnetic field. They are asking for the graph best represents the variation of the magnitude of induced EMF in the loop with the rate of change of the magnetic flux density. By the Faraday's law of electromagnetic induction, the induced EMF is equal to the rate of change of flux. That is capital E. Induced EMF capital E equal delta pi over delta T. Pi is the magnetic flux and pi is given by BA. Pi is equal to BA. Pi magnetic flux, B magnetic flux density, A area covered by the loop. By substituting BA in pi, we have capital E equal delta BA over delta T. A is a constant, that is the area covered by the loop. So we can write E is directly proportional to delta B over delta T, which is equal to R as in the question. So E is directly proportional to capital R. When you look at the graphs given in the answers, we have only one answer showing that E is directly proportional to R, which is the fifth one. So answer is 5. Question number 30. The graph shows how the force on an object varies with the time. They are asking for the correct time for the velocity of the object become 0 again. According to Newton's second law of motion, force is equal to rate of change of momentum. That is F equal mv minus mu over t. Ft equal mv minus mu. At the beginning, u is 0. That the initial velocity is 0. They are asking when would be the velocity become 0 again. That is v is 0. Then mv is 0, mu is 0, then ft also becomes 0. Now this graph is ft graph. The area under the graph is equal to the impulse. So impulse becomes 0. When would be the impulse become 0? Let's take the area under the graph. Area under the ft graph is equal to impulse. Let's take the time from 0 to 40. The area is half times 40 times 8, which is equal to 160. That is the positive side of the graph. Let's take the negative side of the graph. We'll take from 40 to 60. It's a triangle. Area is half times 20 times 8, which is equal to 80. And we want to check for the balance 80. So that is covered by the rectangle. When you take the time 60 to 70, so it is 10 there, into 8, which is equal to 80. Then the total area from 40 to 70 is 160, which matches with the area from 0 to 40. So the total FT, total impulse, that is the algebraic sum of the impulse, becomes 0 at time is 70. So one answer is 70 seconds. Let's consider the rest of the graph, that is from 70 to 100 and 100 to 120. When you look at the areas, these two areas are not equal. So the total FT not become 0 again. So there is only one answer, which is T equals 70 seconds only. That is the second answer, answer 2. Question number 31. 1 million of small spherical droplets of mercury combine and form a large spherical drop. Each small droplet has an electric potential of 0.01. They are asking for the electric potential of the large drop. The electric potential of a sphere is given by Q over 4 pi epsilon naught r. Q is the charge of the sphere, r is the radius. For the small sphere, the electric potential is Q over 4 pi epsilon naught r, and it is given that the electric potential of a small droplet is 0.01. That is Q over 4 pi epsilon naught r is equal to 0.01. And for the large sphere, the electric potential is Q dash over 4 pi epsilon naught r dash. Q dash is the charge of the large sphere, r dash is the radius. Now Q dash must be equal to the million of Q. That is, Q dash is equal 10 to the power 6 Q. We want to find R dash. For that, let's consider the volumes of the spheres. For small sphere, volume is 4 by 3 pi r cube. For large sphere 4 by 3 pi r dash cube. Now the large cube is made up of millions of small droplets. So 4 by 3 pi r dash cube is equal to 4 by 3 pi r cube into 10 to the power 6. Then you get r dash equal 10 to the power square r. By substituting this, you can find the electric potential of the large drop, that is 10 to the power 6 q divided by 4 pi epsilon naught 10 to the power square r, so which is 10 to the power 4 times q over 4 pi epsilon naught r. Q over 4 pi epsilon naught r is 0.01. Then you get 10 to the power 4 multiplied by 0.01, which is equal to 10 to the power 2 volt. That is 100 volt. Answer is 4. Question number 32. A narrow beam of monochromatic light is passing through a prism placed in air. They have given three statements about the angle of minimum deviation, capital D. A. D increases with the increase of refractive index of the material of prism. Consider the equation for the refractive index. Refractive index n equals sin A plus D over 2 divided by sin A over 2. A is the angle of the prism, D is the angle of the minimum deviation. When you look at the equation, it is very clear that n and D has a direct proportionality. That is, when n increases, D increases. A is right. B. D first decreases and then increases with gradual increasing of the angle of incidence. Remember the graph of angle of deviation and angle of incidence. It is a concave curve with a minimum value. That minimum value is the angle of minimum deviation. It is a constant to that context. Only the angle of deviation decreases and increases with the increase of the angle of incidence. B is not right. Then C. D increases with the increase of the angle of prism. You can draw a ray diagram for the angle of minimum deviation. At the state of minimum deviation, the ray diagram is symmetrical. You can mark the angles. Angle of incidence is I. Then angle of emergence is also I. Then angle of refraction from the first surface is R. Then angle of incidence to the second surface is also R. Then by geometry you can write capital A equal R plus R, that is 2R. Capital A equal 2R. Then you can see when A increases, A is prism angle. When A increases, simple R also increase. By the equation n equals sin I over sin R, when R increases, I also should increase since n is a constant. Again by geometry, you can write capital D equal I minus R plus I minus R, which is 2 times of I minus R. If R increases, the increase in I is much more. That is I minus R increases with increase in R. That is when A increases, R increases, I increases and D increases. Ultimately, when A increases, capital D increases. C is right. The answer is 3. Question number 33. A circuit diagram is shown in the figure. They are asking for the value of the internal resistance, simple R, if the power dissipation of each resistor is same. Consider the current in the circuit when the key is connected to 8 ohm is I1 and that is I2 when the key is connected to 2 ohm. By using the Kirchhoff's second law, we can write E equal I1 times 8 plus R. For the I2 current, capital E equal I2 times 2 plus R. By combining the two equations, we can write I1 times 8 plus R equal I2 times 2 plus R. Then the ratio I1 over I2 equal 2 plus R over 8 plus R. Now consider the power dissipation. I1 squared times 8 equal I2 squared times 2. By that you can find the ratio of I1 and I2. I1 over I2 equal 1 over 2. Substituting this in the other equation, we can write 1 over 2 is equal 2 plus R divided by 8 plus R. Then you can find simple R is 4 ohm. Answer is 2. Question number 34. This question is about cooling of an object in air. By using Newton's law of cooling, we know that rate of cooling is proportional to the difference in temperature between the object and the surrounding. That is delta theta over delta T is proportional to theta minus theta R. Delta theta is the temperature difference, delta T is the time taken, theta is the temperature of the object, theta R is the temperature of the surrounding. Let's apply this for the first instance. Delta theta, that is the temperature difference from 60 to 50, 10. Delta T is 5 minutes. Is proportional to theta. Theta is the temperature of the hot object. Now here the temperature changes from 60 to 50. So we take the average 60 plus 50 divided by 2, that is 55. So theta is 55 minus the temperature of the surrounding 30. Then we get 10 divided by 5 is 2 proportional to 55 minus 30, 25. 2 proportional to 25. Then for the second instance, 8, temperature difference is 8 divided by T, the time, proportional to The average temperature is 45 plus 36 divided by 2 is 40. 40 minus 30. 8 by t is proportional to 10. Then we divide the first expression by the second. Then we get 2 divided by 8 by t equal 25 by 10. Then we get t is 10. The answer is 1. Question number 35. What is the maximum mass of ice at minus 5 degrees Celsius that can be completely dissolved in 1 kilogram of water at 35 degrees Celsius in a container with negligible heat capacity? Let's assume the mass of ice needed to absorb all the heat in 1 kilogram of water is simple m. This mass of ice absorbs heat from water to change its temperature. That is minus 5 degrees Celsius becomes 0 degree Celsius ice. Then 0 degree Celsius ice become 0 degree Celsius water by changing its state. So for that process it absorbs heat from water. So that can be calculated by ms delta theta plus ml. ms delta theta, that is m multiplied by s is specific heat capacity of ice, 2 into 10 to the power 3 into temperature change is 0 minus 5 plus ml, m into specific latent heat, 3.4 into 10 to the power 5. That total heat is supplied by the water. ms delta theta, m 1 kilogram, s 4 into 10 to the power 3, temperature change is 35 minus 0. By calculation you get m is 0.4 kilogram, that is 400 gram. Answer 5. Question number 36. This question is about a compound microscope in the normal adjustment. They are asking for the magnification of the eyepiece. The equation for magnifying power of a compound microscope, capital M, equal MO times ME. MO is the linear magnification of the objective lens. ME is the linear magnification of the eyepiece. The question is to find ME. MO can be found by the given data. MO is V divided by U. V is the image distance and U is the distance to the object from the objective lens. Let's take the lens equation. 1 over V minus 1 over U equal 1 over F. We need V over U. For the convenience, we multiply the whole equation by U. Then we get U over V minus 1 equal U over F. Then U over V equal U over F plus 1. Now substitute the values with the sign conversion. Then U is 2.6, F is minus 2.5, V over U. By substituting, you get U over V equal minus 0.1 divided by 2.5. Then V over U, which is equal to MO, is 25. V over U is the reciprocal of U over V. V over U is 25. Now substitute that in our equation. MO times ME equal 100. MO is 25 times ME equal 100. So ME is 4. The answer is 1. Question number 37. A charged particle moving in a circular path perpendicular to a uniform magnetic field penetrates through a thin aluminum sheet as in the figure. If half of the initial kinetic energy is lost due to penetration, they are asking for the radius of the new path of the particle. As the particle is moving in a circular path, the centripetal force can be written as mv squared over r. M is the mass of the particle, v the velocity, and r is the radius of the circular path. And that centripetal force is provided by the magnetic force BQV. BQV equal mv squared over r. By that we get BQ equal mv over r. BQM, all three are constant, so we get V over R is constant. That is, V is directly proportional to R. Now we write the equation for the kinetic energy. Kinetic energy E equal half mv squared. Half and m are constants, so E is proportional to v squared. And we know that v is proportional to r, so we can write E is proportional to r squared. Then for the next instant, the kinetic energy is half of the previous value. E by 2 is proportional, directly proportional to the new r dash square. By dividing the first expression by the second expression, we get 2 equal r square divided by r dash square. Then we get r dash equal r divided by root 2. Answer is 2. Question number 38. An electrical circuit is shown in the figure. Voltmeter and ammeter are ideal and center zero. The battery has negligible resistance. The variable resistor R can be changed from 0 to 100 ohm. They are asking for the ammeter reading and voltmeter reading when the sliding key is at X and at Y. For the convenience to explain, we mark the junction between 40 ohm and 60 ohm as P and the junction below 60 ohm as Q. The line passes through Q, that is the branch, horizontal branch passing through Q has a zero potential because that part is earthed. Now we'll check for the potential differences across 40 ohm and 60 ohm resistors. The battery has 20 volt and that battery supplies the voltages across 40 ohm and 60 ohm. So that 20 volt will be divided across these resistors in the ratio of these resistances. So the potential difference between 40 ohm will be 8 volt and the potential difference across 60 ohm is 12 volt. Since Q is earthed, the potential at P is 12 volt. P is connected to the negative terminal of the voltmeter and key is connected to the positive terminal of the volt. Now let's see what will be the reading of the voltmeter when the key is at X. When the key is at X, there is no potential drop below X. So the potential at X is also 0. Then the potential difference between the key and P is 0 minus 12, which is minus 12. So the voltmeter reading when the key is at X is minus 12 volt. So there are two answers with minus 12 volts. Those are 3 and 5, and let's check for the ammeter reading. Ammeter reading shows the current through the ammeter. Before calculating the current, we find the combined resistance of the circuit. 40 ohm and 60 ohm are in series, so the combined resistance is 100. That 100 and the R are in parallel. The resistance of R is 100, so 100 and 100 are in parallel. Combined resistance is 50. Then we use Kirchhoff's second law to the circuit. That is 20 volt is equal 50 times I. I is 400 milliampere. The answer is 5. Even without checking for the voltmeter reading, when the key is at Y, we can select the answer 5. Question number 39. A metal wire is rigidly clamped at 2 points A and B. When a mass is hung from its midpoint, the midpoint sags from its initial position. They are asking for the approximate value of the Young's modulus of the metal. Let's mark the midpoint of the wire, that is the point where the mass is hung, as C, and tension in each side of the wire as T, and the acute angle, the angle between the vertical and the wire, as theta. Then we consider for the equilibrium of the system. Then that is, upward forces are equal to the downward forces. Upward force, component of T cos theta. For the other side, T cos theta. The total is 2 times T cos theta. That must be equal to mg for the equilibrium. That is 2T cos theta equal mg. Then 2T cos theta equal m is 2.4 into 10. T cos theta is 12. By geometry, we can find cos theta. Cos theta is adjacent side divided by the diagonal. So adjacent side is 2 centimeter divided by diagonal, it is not 1 meter, but we take the approximate value and we consider that diagonal is also 1 meter, because in the question they are asking for the approximate value of the Young modulus. So we can do some approximations in our calculation. So cos theta is 2 into 10 to the power minus 2. Then by substituting for cos theta, we get T is 6 into 10 to the power 2. Then Young modulus is stress over strain. Stress is F over A, force over area. Force is tension, tension over area. Then you get 1.2 into 10 to the power 8. That is, stress is 1.2 into 10 to the power 8. Then strain. Strain is extension over original length. We take this only for one side. Then extension is 0.02 centimeter divided by 1 meter. So the strain is 0.02 into 10 to the power minus 2. Then Young modulus is stress over strain. So you get the answer 6 into 10 to the power 11. The answer is 4. Question number 40. An infinitely long thin straight wire is located on the z-axis, has a linear charge density of minus lambda. A small positive charge is allowed to move in the xy plane in a circular path about the wire. They are asking for the periodic time of the charge. If the electric field strength at a distance r from a wire is E, then we can write the electric force on the charge as EQ. This charge is moving in a circular path, so this electric force must be equal to the centripetal force. Centripetal force is mr omega squared. Electric force is EQ. mr omega squared equal EQ. Omega squared equal EQ over mr. Omega is 2 pi over T. T is the periodic time. By using 2 pi over T in omega, you get an expression for T, that is T equal 4 pi squared mr over EQ. We want to find E now. By using the Gauss theorem, we know that electric field strength at a distance r from a wire of linear charge density lambda is given by E into 2 pi r equal lambda over epsilon naught. Epsilon naught is the permittivity of free space. Then by that we get E equal lambda divided by 2 pi r epsilon naught. By substituting this in lambda, we can find T, which is equal to the answer 1. Question number 41. A horizontal pipe ABC is connected to a water tank with a large cross-sectional area. The internal cross-sectional area of the pipe at B is twice that of at C. Initially, the water tap is closed. They are asking for the height of the water level in the vertical tube once the tap is opened. Assumptions: the water flow is steady and streamlined, and to neglect the viscosity of water. This question is of application of Bernoulli's theorem. Let's consider the rate of flow of water inside the tube ABC. Rate of flow of water is given by A times V. A is the cross-sectional area of the tube. V is the speed of water inside the tube. Now we consider the points B and C. Assume that the area at C is capital A and the speed of water at C is V. Then the rate of flow of water at C is given by A times V. Now we consider the point B. The area of the B is 2 times of A. Then the velocity of water at B must be half of V. The rate of flow of water at B and C is constant. So the velocity of water at B is half of V. Let's apply the Bernoulli's theorem. Bernoulli's theorem is P plus half rho V squared plus rho GH equal constant. P is the pressure, half rho V squared, V is the velocity of the water, plus rho GH, G gravitational acceleration, H the height difference of the stream of water. Let's use this Bernoulli's theorem for the points B and C. Let's take the point C. P plus half rho V squared plus rho GH. P. P is the pressure at C. It is the atmospheric pressure. We use pi for that. Pi plus half rho V squared. The velocity of water at C is V. Then half rho V squared plus rho GH. Rho GH. No height difference in the streamlines, so H is 0. Then for the point C, we have pi plus half rho V squared. Then for the point B, P, pressure at B. If the height of the water column in the vertical pipe is H dash, then the total pressure at B is atmospheric pressure plus the liquid pressure, that is pi plus H dash rho G plus half rho V squared, half rho. Now the velocity at B is half of V, V by 2 squared, half rho V by 2 squared. And there is no height difference in the streamlines, so H is 0. Then for the B point you get pi plus H dash rho G plus half rho V by 2 square. By that you get H dash rho G equal half rho times, put in brackets, V squared minus V by 2 square. By that you get H dash G equal half rho times V squared minus V squared over 4. H dash G equal half times 3V squared over 4. Then we want to find V squared. Let's apply the Bernoulli's theorem for the points A and C again. For the point A, P plus half rho V squared plus rho GH. P atmospheric pressure plus the liquid pressure rho GH plus half rho V squared. Since this is a large tank, the velocity of water at A is considered to be 0. Then half rho V squared is 0. And for rho GH, there is no height difference in the streamlines of water. So H is 0. Then you have phi plus pi rho GH. for the point A equal, now do it for the point C, pi plus half rho v square. By that you get v squared equal 2gh. Now we apply v squared equal to gh in the above equation. Then you get h dash equal half times 3 over 4 times 2gh, that is h dash g equal half times 3 by 4 times 2gh. There you get h dash equal 3 by 4 h. Answer is 3. Question number 42. A parachutist bails out from a helicopter at time t equals 0. After a certain time, he opens his parachute and then reaches the ground. They are asking for the graph best represents the variation of the vertical component of the velocity of the parachutist with time. His velocity is 0 when the time is 0. Each graph is starting from the origin. They show that velocity is 0 when the time is 0. Let's see what will happen to his velocity when he falls down under gravity. If in absence of air, he will fall under constant acceleration, that is gravitational acceleration. If he falls down under a constant acceleration, the answer is more close to the second answer. But in the actual situation, he is falling in air. So there is a air resistive force upward. So due to the air resistive force opposite to the motion of the parachutist, he will falls down with a deceleration. So the answer would be 1 or 5. In the first part of his motion, he falls down in a deceleration. So answer may be 1 or 5. Then what will happen when the parachute is open up? When the parachute is open up, his velocity drops down very quickly. And then he slows down and finally he will come down with a terminal velocity. So when you compare the answers 1 and 5, the 5 is the answer. Answer is 5. Question number 43. They have given 3 statements about the half-life, T-half, of radioactive atoms in a sample. A. T-half changes with the number of radioactive atoms present in the sample. The half-life, T-half, is the time taken by the number of atoms to become half of it. So there is no connection between the half-life and the number of radioactive atoms in the sample. A is wrong. B. T-half changes with date and time of the prepared sample. B is wrong. There is no connection between the half-life and the date and time which the sample is prepared. C. T-half does not change even if the radioactive atoms are ionized. Ionization and radioactivity are two different processes. Ionization happens from the electrons of the outer shells and the radioactivity happens from the nucleus. So there is no connection between radioactivity and ionization. C is correct statement. So the answer is the third one. Question number 44. An electron moves in the plane of the paper through two regions, region 1 and region 2, along the path shown in the figure by broken line. Uniform magnetic fields B1 and B2 exist in regions 1 and 2 respectively. A uniform electric field exists only in region 1. The direction of the electric field is into the plane of the paper. They are asking for the correct directions of magnetic fields in regions 1 and 2. The direction of the electric field is shown by the crosses. Let's consider the region 1 first. So crosses shows the direction of the electric field is into the book. That is, force on a positive charge is into the book. The electric force on positive charges is into the book. This is an electron moving from left to right in region 1. So the electric force on the electron is a negative charge. The electric force on the negative charge is outside the book. If there is a force outside the book, the electron will not move in a straight line as shown in the figure. So, to keep the electron moving in the straight line as shown in the figure, there must be another force which is opposite in direction to the electric force. So, that is the magnetic force. Magnetic force on the electrons must be into the book. As the electrons are moving from left to right, the positive charges are to be considered moving from right to left. Magnetic force on the electrons which are moving from left to right is into the book. Similarly, the positive charges are moving from right to left, subjected to the magnetic force directed into the book. To find the direction of the magnetic field, you can use Fleming's left hand rule. Keep the first three fingers of the left hand perpendicular to each other. Then thumb is pointing to the direction of the magnetic force and the second finger is pointing to the direction of the magnetic field, and the middle finger is pointing to the direction of the motion of the positive charges. Now, when you keep your three fingers perpendicular as described, point your thumb into the book and the middle finger to the left, then the second finger will be pointing upwards along the paper, along the book. So that shows the second finger is showing the direction of the magnetic field. So when you look at the answers, you can find two answers which are showing B1, that is the direction of the magnetic field is upward along the book. Those two answers are 1 and 2. Now let's consider the region 2. There the electron is moving in a semicircular path. The direction is shown by the arrows. To find the magnetic field, you can also use the Fleming's left hand rule. Since this is moving in a circular path, the magnetic force on the charge must be towards the center of the circle. That is, the electron is moving as shown in the dashed lines. The magnetic force on the electron is to the center of the circle. You can use Fleming's left hand rule to find the direction of the magnetic field. You can keep your three fingers of the left hand perpendicular to each other as described before, and your thumb to the direction of the force which is towards the center of the circle, and point your middle finger to the direction of the motion of the electron. Then you can find that your second finger is pointing downwards, that is pointing into the book. So that is the direction of the magnetic field is inside if this charge is a positive charge. Since this is a negative charge, to keep the path as shown in the figure, the magnetic field must be outside the book. That is answer 2. Question number 45. Figure shows a capillary tube dipped vertically in a container of water with a large cross-sectional area. The system is fixed in an elevator at rest. The open end of the capillary is 40 mm above the water level of the container and the capillary rise is 8 mm. They are asking for the respective capillary rise if the elevator is moving downwards and also if the elevator is falling freely. Capillary action occurs when the adhesive to the surface material is stronger than the cohesive forces between the water molecules. The height to which capillary action will take water is limited by the surface tension and gravity. Water wants to stick to the glass and surface tension will push the water up until the force of gravity prevents further rise. Let's write the equation for the above situation. That is, upward force is equal to the weight of the water column. Upward force is the surface tension that is given by T times 2 pi r. Weight of the water column is pi r squared h dg. T times 2 pi r equal pi r squared h dg. T is the coefficient of surface tension, r radius of the tube, d density of the water, g gravitational acceleration, h height of the water column. So by this equation, T equal to pi r equal pi r squared h dg. We get h equal 2 times T divided by r dg. Since T, r, d are constants for the given situation, we can write h is proportional to 1 over g. That is, we can see that h, the height of the water column, changes with the acceleration of the system. Let's consider the first instance. We can mark the forces on the diagram. Mg, that is the weight of the system downward, normal force capital R upward. Using F equal ma downwards, we can write mg minus r equal ma. R equal m times g minus a. G is the gravitational acceleration, which is equal to 10, and a is the acceleration of the system, that is 5. So we get m 10 minus 5, that is m times 5. R equal m times 5. So that is the effective acceleration when it is moving down with an acceleration is 5. With the relationship h is proportional to 1 over g, for the initial situation we can write the capillary rise is 8 millimeter. 8 is proportional to 1 over, the acceleration is 10, 1 over 10. For the next situation, if the capillary rise is h dash is proportional to 1 over the acceleration, the effective acceleration is 5. H dash proportional to 1 over 5. By dividing one by the other, we can write 8 divided by h dash equal 5 divided by 10. There you get h dash equal 16 millimeter. Let's consider the second situation. There the system is falling down freely. That is, it's falling down with the gravitational acceleration. So we use F equal ma for the system. Mg minus r equal ma. R equal m times g minus a. G is 10 and acceleration is 10. G 10 minus 10 equals 0. So we get r equal m times 0. Effective acceleration is 0. By the relationship h is proportional to 1 over g, if the capillary rise is h double dash, we can write h double dash is proportional to 1 over 0, which is infinity. H reaches infinity when the system is falling down freely. But the maximum height of the tube is 40 millimeter. So it cannot rise beyond 40 millimeter. So the water height of the water column would be 40 millimeter. Answer is 5. Question number 46. Two vertical glass tubes T1 and T2 filled with the liquid are connected at their lower ends by a horizontal capillary tube. T1 is surrounded by a mixture of ice and water at 0 degrees Celsius, and T2 is surrounded by water kept at constant temperature 40 degrees Celsius. Difference in heights of the liquid is given, and the height of the liquid column at 0 degrees Celsius is also given. They are asking for the real volume expansivity of the liquid. We know the liquid pressure at the same level of the same liquid is equal. We use this concept to solve the problem. We consider that the atmospheric pressure is pi and the height of the liquid column at T1 is H1 and the density of the liquid in T1 is ρ1, and for T2 the height is H2 and the density of the liquid is ρ2, and the temperature difference is 40 minus 0. Gamma is the volume, real volume expansivity of the liquid. We write the pressure at the bottom of the T1. So we get pi plus H1 ρ1 g. For T2 it is pi plus H2 ρ2 g. The densities are different in the two tubes because they are at different temperatures. So we can equate the two pressures at the bottom of the tubes. Pi plus H1 rho 1 G equal pi plus H2 rho 2 G. By that we get H1 rho 1 G equal H2 rho 2 G. Then we get H1 rho 1 equal H2 rho 2. And also we know that the density of the first one, that is rho 1, is equal to rho 2 times 1 plus gamma delta theta. We substitute this relationship in the above equation, that is H1. For rho 1 we put rho 2 times 1 plus gamma delta theta equal H2 rho 2. They are rho 2 being cancelled. Then we get H1 times 1 plus gamma delta theta equal H2. H1 is 80 centimeter. 80 times 1 plus gamma delta theta is the temperature difference, that is 40 minus 0, which is equal to 40, equal H2 is 81.6. So we get 80 times 1 plus gamma times 40 equal 81.6. Then we get 1 plus gamma times 40 equal 81.6 divided by 80. Then gamma times 40 is equal 1.6 divided by 80. Then gamma become 5 times 10 to the power minus 4. Answer is 2. Question number 47. Figure shows an infinite ladder network of 1 ohm resistors. They are asking for the correct answer if the equivalent resistance of this network between points A and B is R. When you look at the diagram, you can see that 1 ohm resistor is directly connected to A terminal and another 1 ohm resistor is directly connected to B terminal, and the other set of resistors are connected in between these two resistors. So definitely the total resistance of this network must be greater than 2 ohm. That is 1 ohm plus the resultant of the other network of resistors plus 1 ohm. That is 1 ohm connected to A plus the resultant of the network of other resistors plus the 1 ohm connected to B. So that is definitely the resultant would be greater than 2 ohm. And we'll see the resultant of the other 1 ohm resistors connected in parallel. You know, when the resistors are connected in parallel, the resultant resistance would be smaller than the smallest resistance in the network. So the resultant of the 1 ohm resistors connected in this network should be smaller than 1 ohm. So the resultant of the whole set of resistors would be smaller than 3 ohm. That is 1 ohm plus less than 1 ohm plus 1 ohm. The answer would be 5. Question number 48. 3 stars, each of mass m, are at the vertices of an equilateral triangle as shown in the figure. These 3 stars rotate in a circular path about the centroid of the triangle. The initial distances among the stars remain unchanged. If only the mutual gravitational forces are acting among the stars, they are asking for the periodic time of the system. For the convenience, we take these masses as A, B, C. First, we consider the mass A. The force of attraction between A and B can be written by using the Newton's law of gravitation. F equal capital G times the product of the masses divided by the square of the separation. That is, we mark this force as FB. FB equal capital G simple m times simple m divided by A square. Then we take the attractive force between A and C. The attractive force on A by C is Fc is also equal to capital G times simple M times simple M divided by A square. So the two forces acting on A by B and C are Fb and Fc. These Fb and Fc forces are along the sides of the triangle, resultant towards the centroid of the triangle. Then we have to take the components in the direction of the centroid, that is Fb cos 30 plus Fc cos 30. Since Fb and Fc are common, we can write 2 times G simple m divided by A square cos 30 equal the centripetal force. Centripetal force is given by mr omega square. That is, the centripetal force is provided by the gravitational force towards the centroid of the triangle, that is 2 times capital G m into m divided by A square cos 30 equal m r omega square. R is the distance from A to the centroid. So that can be found by using trigonometry. 2 times of cos 30 equal A. Then R equal A divided by 2 cos 30. By substituting this in the above equation, we have 2 times of capital G times m divided by A square cos 30 equal m times, instead of r we put A divided by 2 cos 30 into omega square. Then we have 2 times capital G m divided by A square cos 30 equal A divided by 2 cos 30 into omega square. By that we get omega square equal 4 capital G m divided by A cube times cos 30 square. That is 4 times G times m times cos 30 square divided by A cube. By substituting the value for cos 30, we get omega square equal capital G m divided by A cube into 3. That is omega square equal 3 times G m divided by A cube. Omega is 2 pi over t. So we use 2 pi over t for omega. Then you get 2 pi over t square equal 3 times Gm over A cube. Then you can find t square. T square equal 4 pi square times A to the power 3 divided by 3 times G times m. Then t equal 2 pi square root of A cube divided by 3gm. Answer is 2. Question number 49. A block A of mass 2 kg and block B of mass 6 kg are placed on a frictionless horizontal surface. 2 identical springs of negligible mass are fixed to the blocks as shown in the figure. Block A is projected with speed 2 meter per second towards block B, which is at rest. They are asking for the maximum energy that the 2 springs could attain. The springs attain the maximum energy when their contraction is maximum. Their contraction is maximum when A and B are in contact. That is, firstly, the 2 kilogram mass is moving at a 2 meter per second velocity and connects with B. So at that time, the springs will have the maximum contraction. So at that time, A and B move together. We'll use the conservation of momentum before and after the collision. Before collision, The momentum of A is mass times velocity, that is 2 times 2, 4. And momentum of B is 0. After collision, A and B are in contact. They move together with a velocity v. The total momentum is mass times velocity. Mass is 2 plus 6, that is 8 kilogram, into v. So by using the conservation of momentum, we get the momentum, initial momentum is 4 equal final momentum 8 into v. So there we get v equal half. Then we check for the kinetic energy. Before collision, A has kinetic energy given by half mv squared, that is half into 2 into 2 square, that is equal to 4. Then kinetic energy after collision, half times mass is 8 times v is half square, it is 1. The change in kinetic energy is 4 minus 1, which is equal to 3 joule. The kinetic energy before collision was 4 and kinetic energy after collision is 1. These kinetic energies are possessed by the masses. So the lost kinetic energy will be gained by the springs. So the maximum energy of the two springs attained is 3 joule. Answer 4. Question number 50. 5 thin flat metal plates, each of area A, are kept parallelly in vacuum with an equal gap, simple D. If plate P is connected to S and plate R is connected to T using conducting wires, as in the figure, they are asking for the equivalent capacitance between terminals X and Y. For the explanation purpose, we draw an equivalent diagram in a different way. First we draw the P plate by a line and then Q plate parallel to P, but Q plate is connected to the terminal X, so we split the Q plate into two parts having the same cross-sectional area. We drew P plate, then in parallel to P we drew Q plate, and the next Q plate. These two Q plates are connected by a cross line, and in between that line, that cross line has X terminal. So you mark X in between the cross line. Now we drew P plate and two Q plates, and then the R plate parallel to Q. We split R also into two, having the same cross-sectional area. So two R plates. The two R plates are connected by a cross line, and in between it has Y terminal, and then S plate parallel to R. S plate also split it into two, that is also connected by a cross line. Then T plate parallel to S. So your diagram has P plate, then parallel to P, Q plate, and another Q plate parallel to that Q. These two Qs are connected by a cross line. Then R plate parallel to Q. Then the next R plate parallel to that R, and those two R's are connected by a cross line. And then S plate, then the other S plate. These two S's are connected by a cross line. Then T plate. And before the P plate, you can draw a cross line and mark a point A there. After the T plate, draw a cross line and mark the point B there. And in between the cross line which connects two S's is C. Before the P plate, you can draw a cross line and mark a point A there. After the T plate, draw cross line and mark the point B there. And in between the cross line which connects two S's is C. I put additional symbols to make the explanation easy. When you look at the diagram, you can see, okay, before that, we mark these capacitors from 1 to 4. The first capacitor is made up of P and Q plates. P and 1 Q plate. Second one is made up of Q and R. Then third one is made up of R and S. Then fourth one is made up of S and T. When you look at the diagram, you can see you take the 3 and 4 capacitors first. Look at the 3 and 4 capacitors first. That 3 and 4 is connected to the terminal C, and since Y and B are connected together, they both are having the same potential. So we can consider that 3 and 4 capacitors are in parallel. If 3 and 4 are in parallel and the capacitance of the each capacitor is C, then the combined capacitance of 3 and 4 is 2C. The capacitance of the first one is C, capacitance of the second one is C, and capacitance of the combined capacitors of 3 and 4 is 2C. Now simplify your diagram. You draw the first capacitor, then the second capacitor, then the new capacitor which formed by the capacitors 3 and 4. So they all are combined by cross lines. And now the X point is in between the two Q plates, and Y point is in between two R plates. Then A and C points are there which we marked additionally. You can see the first capacitor and the last capacitor, that is first capacitor of capacitance C and the last capacitor of capacitance 2C are in series. So the combined capacitance is calculated by taking the reciprocals. If the combined capacitance is C dash, we can write 1 over C dash equal 1 over C plus 1 over 2C. Then C dash is equal 2C over 3. Now you can see that the combined capacitance of that and the second capacitor is in parallel. So you can find the equivalent capacitance of these two capacitors, that is capacitor 2 and the combined capacitance of 2C over 3 are in parallel. So we take the addition of the capacitance to find the combined capacitance, that is C plus 2C over 3, that is 5C over 3. C is given by epsilon naught times A divided by D. By substituting that in the above statement, we have 5 over 3 times epsilon naught A over D. Answer is 2. Thank you. Subscribe the channel to get more videos.